In today's lecture, we will be discussing about chemical kinetics. This video consists of introduction to chemical kinetics and various orders of reaction, reaction rate constants, and determination of half-life. Before we get into the lecture, we need to know how this chemical kinetics is related to physical pharmacy course and how far this concept is important to a pharmacist. The chemical kinetics, the name itself indicates kinetics, which is related to a speed. Chemical kinetics is a term used to know, or it is a term which explains the speed of a reaction, the rate of a reaction. So you can define chemical kinetics as a study of the speed of chemical reaction taking place, the rate of chemical changes. Now, how this chemical kinetics topics is helpful for a pharmacist during the drug and dosage form preparations, and during the storage, during the stability testing of a formulation, we need to study or we need to check for any physical or chemical changes that occur in the formulation. And also this concept is very much useful to determine the shelf life of a dosage form. That is how this is very important for a pharmacist. It is useful to study the stability of a formulation and also to predict or determine the shelf life of a formulation. By studying the kinetics, we will be able to know the rate of the reaction. And that is how we can easily know how fast our drug is going to get degraded in the product during its shelf life. Now, how long that product or a formulation can be stored, avoiding degradation reactions. That is how this chemical kinetics have applications in the pharmaceutical field. Now, let's get into the rates and orders of the reaction. The rate of the reaction, the name itself indicates how far or how fast a reaction takes place, is explained by the concept rate of reaction. So the rate of reaction is defined as the velocity or the rate with which the reactants undergo chemical change. Normally, for example, let's consider a reaction A and B. So, for example, reaction A and B. So, A is the reactant, B is the product, and the reaction takes place. The rate at which this reaction takes place is known as reaction rate. And here we need to know about few terms called C is a concentration of the reactant. B. C again, the concentration of the product. Now, dc by dt represents the change in the concentration with respect to the change in the time. As we are discussing about the change in the concentration of the reactants, so dc, change in the concentration of the reactant by change in the time. So as the reaction proceeds further, there will be some change in the concentration of A, right? So this change in the concentration, there will be a decrease in the A concentration, and at the same time there will be increase in the B concentration. So the change in the concentration with respect to time is known as reaction rate. If there is a greater decrease in the concentration of A, means with respect to time, then it will be, we can say like it is having a faster reaction rate. So that is how we can know the reaction rate. So we can say like dc by dt gives the reaction rate. Now here we need to consider the signs plus or minus. So here minus indicates the decreased concentration and plus indicates the increased concentration. So when we look into this particular reaction, now here minus dc by dt, and if we are considering the concentration of products, of course it'll be a positive sign, dc by dt. So minus indicates decrease in the concentration, and plus indicates increase in the concentration with respect to time interval. So now coming to the units, it is very much important to always write down the units. It's always moles per liter. So dc by dt. So dc by dt. So dc is the concentration of the reactants in the particular volume or volume of a solution, means moles per liter, dc by dt, always to be in seconds. So the unit for the reaction rate would be moles per liter per second. So moles per liter per second. So that is how we need to even note down the units. Now let's get into the reaction. Now let's take a reaction into consideration. Like here we have taken A and B reactants, and it has undergone some reaction to produce or to give products. Now here small a and small b represents the number of moles of reactant A, number of moles, B represents the number of moles of reactant B participating in the reaction. Now, if we consider the number of moles of reactant, then the rate of the reaction can be given by the rate is equals to, as we all know, minus dA by dt, right? So V number of moles gives rise to products. Now the reaction rate is given by rate is equals to normally minus, so the concentration term by dt, right? Now, as we need to even consider the number of moles, so our reaction, the formula turns out to be 1 by small a. So this is how we can even incorporate the number of moles, and thus we can get the reaction rate equation. Similarly, we'll be going with the rate is equals to minus 1 by b into d concentration terms of b by dt. So when we put these together, because we are having two reactants, then our the equation turns out to be like when we consider for both A and B, the reaction turns out to be reaction rate is equals to K. It's a constant terms of A, concentration terms of B, the number of moles of reactant A, number of moles of reactant B. So the reaction rate constant can be given by equals to reaction rate is equals to reaction rate constant into the concentration terms of A, concentration terms of B. And the power represents the number of moles of A and B respectively. And here the most important thing is the number of moles of A and B, here A. The summation of A and B represents the order of the reaction. The order of the reaction. So to always remember, we need to sum up the number of moles of the reactants participating in a reaction to get the order of a reaction. So what is actually, how far this order of reaction is important? Now let's get into the point. Let's see. We'll check the molecularity of a reaction. As you all know, the molecularity, the name itself indicates the number of molecules participating in the reaction. If there is only one molecule that is participating in the reaction, then it is known as unimolecular reaction. Let me give one example. So unimolecular reaction here, one molecule of bromine reacts and it produces the product. It's only one molecule of a substance. Similarly, if there are two molecules participating to get the product, then it is known as bimolecular reaction. It's as simple as that. But then it is the order of reaction that actually plays a major role to study the reaction, to study the reaction rate. Now let's see one by one. Now we will discuss about zero order reaction. The zero order reaction, the name itself indicates here, the reaction rate is not dependent on the concentration terms. Let me explain through an equation. See, as we all know, rate is equals to, when we consider A and B as the reactants, B, so A number of moles of and B number of moles. So to know the reaction, to know the order of this particular reaction, now we will be summing up these two values, right? Number of moles of reactant A, number of moles of reactant B, that gives the order of reaction. But when we are discussing about the zero order reaction, now the reaction rate is not dependent on the concentration terms. It will, as such, the chemical reaction will proceed as such. It is not dependent on the concentration terms. So we will be not using any, we don't have that uh, parameter. So simple, the reaction rate is equals to K in case of zero order reaction. So the reaction rate would be minus dC by dt is equals to K. So in few journals or textbooks, even this C, the concentration term C, is represented as A also, which represents the change in the concentration with respect to time is equals to reaction rate constant. The negative sign indicates the concentration term is being decreased. A, for example, A, giving rise to products. So it will decrease with as the time passes by. So this is how the reaction rate constant for a zero order reaction can be considered. Now let's see what are the units, what will be the units for the rate constants of different orders of a reaction. For a zero order reaction, minus dC by dt equals to K, right? So this K is equals to minus dC by dt. We will be not considering this. So what is the unit for dC normally? Moles per liter. So moles per liter per second. So moles per liter per second. The units of a rate constant is very important. When we are calculating the reaction rate, it is always must to include these units. And also in most of the practical problems, if you are given to solve, then based on these units we can come to know what kind of order of reaction it is, what kind of order the reaction is following. Sometimes we will be not given that in this particular zero order of reaction calculate the rate constant. No, we'll be not told like that. Instead, we will be given a value along with units, and we will be asked to know whether the following reaction follows zero order or first order or second order. So if we get to know the units, we can easily answer such kind of questions, especially in case of the competitive examinations. Now let's see how can we know the units for the first order reaction. dC by dt is equals to K into concentration terms 1. First order reaction. The summation of the powers on the number of moles reacting in the reaction is the order. So K is equals to dC by dt by the concentration terms, right? So dC by dt, dC by mole per second, mole per liter per second. So this will be dC by dt into, again the concentration term, it will be mole per second, mole per liter. So this turns out to be the numerator, this turns out to be denominator, right? So now the L gets cancelled, mole gets cancelled. So the unit for the first order reaction rate constant would be second inverse, right? So based on the units, it'll be very much easy for us to identify the order of the given reaction. That's how we can even solve for the second order reaction. dC by dt is equals to K into concentration terms of A power of 2. So dC by dt, when this comes this way, it'll be in the denominator. So concentration terms of A square. So as usual, dC by dt mole per liter per second into the same. It gets inversed, right? So liter square by mole square. So one cancel. This one of the L gets cancelled. So we'll be having liter per mole per second. So this is the unit for the second order reaction, the reaction rate constant units. So this is how we can determine the units. Now let's get into the zero order reaction. How we can solve this as a linear expression or a linear equation. Let's see. Zero order reaction is a reaction in which the reaction rate is independent of the concentration of the reactants, right? So dC by dt is equals to K naught into A to the power of 0. So dC by dt is equals to K naught. That we already know. Now let's see as we are discussing about the reaction rate, which reaction rate here indicates the change of the concentration of reactants with respect to time interval. Means, for example, in the first 5 minutes of a chemical reaction, the reaction speed will be different, right? Now what are the changes that are going to occur in the reaction at the first particular time interval and the next particular time interval? So to know that particular change with respect to time, for that we need to actually integrate this rate law. Normally this equation is known as rate law. The change in the concentration with respect to time is equals to rate constant, and the product of the concentration of reactants, that particular equation is known as rate law. We need to integrate this rate law between the initial concentrations, like at the beginning of the reaction, and at the particular time interval where we need to check its reaction rate. So it will be C naught, the initial concentration, and the time interval, the concentration at that particular time interval. So it will be CT. So integrate C naught CT is equals to K naught into dt. So we have actually taken this dt term onto the right hand side. So dc is equals to K naught into dt. So we are integrating because we are actually calculating in the particular time interval. So the initial time interval, initial concentration, and the concentration of the after particular time interval. So in order to put this as a linear equation, Ct, I mean the concentration of that at that particular time interval minus C naught is equals to Q naught into T. This represents a zero order rate constant. And now here, why we are taking only just T? Because At the initial time interval, of course, T naught would be 0. So it is only at the particular time interval where we are supposed to measure, or we are supposed to calculate the reaction rate. So our equation turns out to be Ct minus C naught is equals to K naught into T. Now let's see. At particular time interval. So we have taken time interval on x-axis and the concentration of products on y-axis. Now we are discussing about a reaction in which A is a reactant, B is a product. So during this equation or during this reaction, of course, the concentration of the products will be increasing. The concentration, product B concentration will be increasing with respect to time. And whereas for the concentration of A would be decreasing. It will be like this. Now, what is the purpose of this representation, graphical representation, is to make you understand that the rate of product B production will differ at different time intervals. See the concentration, the product concentration with respect to time interval, with this time interval, with this time interval. And when we check the same with the concentration of A, the drug concentration when it is taken on y-axis and time on x-axis, of course the concentration of the reactant will be decreasing. And do always remember, when we are speaking about the reactants here, indicates the drug or the drug products, because we being a pharmacist, we are actually applying this chemical kinetics to the drug, the chemical changes that occur in the drug during its storage or during its formulation or during its stability study, how far it is going to degrade, or how fast our product or how fast our drug is going to get degraded. That is how we can actually predict the shelf life of the drug or the drug product. So do always remember, when we are speaking about the reactants, it is not just a chemical species. It is our drug's chemical species, our drug species, our active pharmaceutical ingredient. So now how we can use this equation, the reaction rate law, in determining the half-life. So first of all, we need to know what half-life denotes. Half-life of a drug, the name itself indicates the time taken for the drug to get dropped to half of its original value. Means, for example, if the drug is 100 mg and after some reaction the product gets gets 250 mg, say. Now the time required for this drop down of the reactants to half of the original value is known as the half-life of a drug in the formulation. Now how can we make use of this rate constant or the rate law in determining the half-life that we are going to see now? We are already having this equation. Now we are discussing about the zero order reaction. Ct is equals to C naught minus K naught into T. So this equation is derived from this equation. Now, from the definition of half-life, now how can we modify this equation? half-life is at that particular time interval, half of the time, at particular time interval, the concentration terms should be exactly half, right? So if this is the concentration terms in at the beginning of the reaction, and of course at that particular time interval, this has to be C0 by 2, right? Because half of its original volume. C0 by 2 is equals to C0 minus K0 into T. T here we can write as T half because we have already calculated this term as C0. So now when we take this term to this side and this term to this side, so C0 minus C0 by 2 is equals to, so 1 minus 0.5 is equals to how much? 0.5, right? So 1C minus C. 1C0, sorry. So 1C0 minus 1 by 2 C0. How much it will be? 1 by 2 C0, right? So 1 by 2 C0 is equals to K0 into T half. I mean nothing but T 0.5. It's nothing but T half. So T half is equals to C0. So this gets to this side. C0 by 2 into K0. That is how we are going to calculate the half-life for this kind of reaction, zero order reaction. T half of the zero order reaction is equals to the initial concentration of the reactants by 2 into the reaction rate constant. How we are going to calculate the reaction rate constant, that we will be seeing further. Okay, this is how we need to calculate the half-life for a zero order reaction. In most of the practical problems, you'll be asked like this, like calculate the half-life for the following reaction, having the initial concentration of the reactant to be like dash moles per liter, and you'll be given this value, the reaction rate constant. So in such cases, you need to take down the concentration given and the reaction rate constant given. Incorporate those values in this equation and you will get to have the half-life of that particular reaction. That is how you will be asked to calculate the half-life. And next, we will be discussing about first order reaction. Now let's see. So as we all know, for example, if we take a time on the x-axis and the concentration terms on y-axis, the hydrogen peroxide slowly gets degraded to form water and oxygen. It will be decreasing, right? The reactants will be decreasing. Now, it is the number of moles of one particular species denotes the order of reaction. Now let's see how what is the exact rate law for this first order reaction. So minus dC by dt is equals to K into C. This is a generalized rate law for first order reaction. Now when we incorporate this rate law for the above reaction, minus dC here represents the concentration of hydrogen peroxide by dt is equals to K into the concentration terms of the reactant, concentration term of the reactant. Now just like we have done the integration from integration between the initial concentration and the concentration at that particular time interval. Similarly, if we do the same thing in this first order reaction, we'll get to have this one. So dc, now let's take the concentration terms on one side and the time terms on the other side. So dc by the c again. So to make it simple, dc by c is equals to k into dt. So this we are supposed to integrate this. So dc by c, the concentration terms of this one, is equals to minus k into dt. Minus represents a decrease in the reactance concentration, minus k into dt. We are integrating as usual. The time interval at the beginning will be 0, so it will be minus kt, integration of c minus integration of c naught, initial concentration, and this represents the concentration of that particular time interval. So integration of c is minus integration of c naught is equals to minus kt. So integration of c is equals to integration from c naught minus kt. We have taken this onto the other side. Now to make this much simplified way, we need to actually convert this to a logarithmic equation. So do always remember, when we are supposed to convert it, log c is equals to log c naught minus kt by 2.303. So when we are converting this integration equation to a logarithmic scale, so log c equals to log c naught minus k by 2.303. To make it simple again, to take out this log, c is equals to c naught. Here, when we are taking out log, do always remember in any mathematical equations, and again if we wanted to make it as a linear one, now it turns out to be the exponential form e minus kt. So this represents the concentration decreases exponentially with time. Now, what is really important, why this conversion into a linear equation is really important? Because in order to know the half-life, and again in order to know the reaction rate constant for a given reaction, it has to be a linear expression, because it will be much helpful for us to plot a graph, and thus the calculations becomes much easier. And when we during this conversion we to the base 10, the equation turns out to be like this. Now let's see. So why conversion to a linear expression is really important, that we are going to see now. Now we will be taking the reactant concentration on the y-axis and the time on the x-axis. So we will be getting a graph like this, as the concentration will be keep on decreasing. Now Here, if we take a slope, so this we can make use of even this equation for calculating the parameters, because our aim is always like we need to consider y equals to mx plus c or minus c, mx plus c. So this is a linear equation where c is the constant, right? And x is x, y are the terms on the y-axis, terms on x-axis, where m represents the slope. Hope you remember this equation, the linear equation. So our aim is to know the slope of the equation. Now, so y equals mx plus c. Now here we will be calculating the slope of this graph. The slope, the value which we get, x, say x, say x. So this slope value is equals to k by 2.303. 2.303. So from this, actually from this graph, we will be able to determine the rate constant. How? By cross multiplying this value from the graph into 2.303 is equals to k, and thus from this equation we will be able to determine the k value, and of course the y-intercept would be c naught, the initial concentration. See, initial concentration, slowly it gets decreased. So from this kind of graphical plot we are able to determine, of course, the c naught and the changes ct also. So if we draw y-intercepts at each time interval, we will be able to determine ct at ct1, ct2 like this. That is how we can determine or we can calculate the rate constant for the given reaction by use of rate law. Now, how can we determine the half-life for this first order reaction? We'll be doing the same way. So integration c minus integration c naught is equals to minus kt. Right? Now take these terms. Like multiplying by minus on both sides. So if we multiply minus on both sides, so it becomes positive, and this becomes positive, and this becomes negative. So our equation turns out to be like this. See, integration c naught minus integration c is equals to kt. So integration just like this. What is log a minus log b? Log a by b, right? Similarly, integration of c naught by c is equals to kt. So c naught, the initial concentration, by what is c? Half of its initial concentration, right? Means 0.5 of the initial concentration, because we are calculating t half, is equals to k into t half. So gets cancelled. Integration of 2 see 1 by 0.5 means 5 by 10, right? 2. So what is integration of 2? Integration of 2 is 0.693. So 0.693 is equals to k into t half is equal to 0.693 by k. So this is the final formula that we will be using to determine the half-life of a first order reaction. That is how we will be getting this value 0.693. So how can we determine k? But from the graphical plot. Say if this is the graph, if this is the thing, here we'll be taking time on x-axis and concentration terms on y-axis, and we need to plot a graph, and then we need to calculate the slope. The slope is equals to k by 2.303. So from this graph we will be getting k. We'll get to know k value. Now that k value, if we incorporate that value in this equation, we'll get to know t half. So in order to know the half-life, we first need to have that graphical plot. It's as simple as that. This is how we will be calculating the half-life for the first order reaction. Similarly, we need to calculate for even the second order reaction. Just like the zero order reaction, it's rate law. From the rate law, how we have determined half-life, and from the rate law of first order reaction, how we have determined the half-life. Similarly, from the rate law of second order reaction, we can determine the half-life. This is the basic concept of chemical kinetics and how we can determine the half-life from these rate laws. And this is how we can apply to the pharmaceutical sciences to determine the half-life of a drug or the drug product. And thus we can determine how fast our drug gets degraded. So in today's lecture, we have discussed about the orders of reaction, the importance of chemical kinetics, the rate law, the half-life calculations for zero and first order reaction. The same way we can carry out for the second order reaction. And if you're having any doubts, you can contact me through my mail. Thank you.